Now, we also are going to see in this section probabilities that are called at least probabilities. I should have had a quote on both sides of that. At least probability. Probabilities involving the phrase at least can often be computed using the complement rule. So here's the idea. Part A of this example. Suppose a coin is flipped twice. What is the probability the coin will land on tails at least once? So the probability of at least one tails is what we're trying to figure out. Well, back on the previous page here, we found out the probability of both of the flips landing on heads. It was 1/4. So the simplest way to figure out this probability of getting at least one tails is to think about the complement. The complement of at least one tails would be no tails or 0 tails. So the complement of flipping at least one tails is flipping 0 tails. So if I take 1 minus the probability of 0 tails, that would give me this probability. So I'm using the complement rule. 1 minus the complement of at least one tail. Now 0 tails is equivalent to saying both heads. So again, back here on this problem, we asked what's the probability it will land on heads both times? Well, if I have both heads, that means 0 tails. So this would be 1 minus 1/4, again, because the probability of both heads, which is equivalent to 0 tails, is 1/4, which means the probability is 3/4. So if I flip a coin twice, the probability that it will land on tails at least once is 3/4. Now again, I could also figure out this probability by looking at the sample space. So this was the sample space. So at least one tails, this has at least one tails, this has at least one tails, this has at least one tails. So there are 3 ways to get at least one tails, only one way to get no tails. That probability is 3/4. This complement rule, though, allows me to figure out this probability without having to list the entire sample space. That's the benefit of it. Suppose the coin is flipped 3 times. What is the probability the coin will land on tails at least once? Well, it's basically the same problem. The probability of at least one tails in my 3 flips, again, it's an at least probability, would be 1 minus the probability of 0 tails, because 0 tails is the complement of at least one tails. Up here, we figured out that the probability of all 3 flips being heads, which is equivalent to saying there's 0 tails, is 1/8. So we would have 1 minus 1/8, which would be 7/8. So the probability of at least one tails would be 7/8. Again, we could have also figured that out here because there's at least one tails, 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 at least one tails. So there are 7 ways of getting at least one tails. So 7 out of 8 would be the probability. Again, the complement rule here for this at least probability allows me to figure this out without having to list the sample space. That's the benefit. Take a look at the last example that I have for this section. The probability that a randomly selected 40-year-old female will live to be 41 years old is 0.99855, according to the National Vital Statistics Report, Volume 56, Number 9. So if you are a 40-year-old female that's pretty good news, right? The chances of you living to be 41 if you're 40 is 0.99855. Now that's for females. It would be different for males. But anyway, almost certain. So we have three parts here. A, what is the probability that 2 randomly selected 40-year-old females will live to be 41? B, what is the probability that 5 randomly selected 40-year-old females will live to be 41 years old? C, what is the probability that at least one of the 5 randomly selected 40-year-old females will not live to be 41 years old? Would it be unusual if at least one of the 5 randomly selected 40-year-old females did not live to be 41 years old? So for part A, we're picking 2 random 40-year-old females. And we want to know what's the probability that the first female lives to be 41 and the second female also lives to be 41. Now, because we are randomly selecting these 2 40-year-old females, we will assume that these 2 40-year-old females are independent from each other. So it's not like they're sisters or twins or anything like that, cousins, where there could be some kind of a dependence possibly. If they're independent, then I can find this probability just by multiplying. So this is going to equal the probability that the first 40-year-old female lives to be 41 times the probability that the second 40-year-old female also lives to be 41. Now, the probability that the first female lives to be 41 is going to be 0.99855. So this is 0.99855. The probability that the second female lives to be 41 is also 0.99855. So if I pull in my calculator, 0.99855 times 0.99855, that is 0.99710 if I round to 5 places. So this is approximately 0.99710. That is the probability that if I randomly select 2 40-year-old females, that both will live to be 41. So pretty likely, right? Almost certain. B, what is the probability that 5 randomly selected 40-year-old females will live to be 41 years old? So now I'm randomly picking 5, and the question is, what's the probability that all 5 will live to be 41? So I'm not going to write down as much this time. I'm going to say, what's the probability all 5 live to be 41? So in other words, what's the probability the first woman lives to be 41, and the second lives to be 41, and the third lives to be 41, and the fourth lives to be 41, and the fifth lives to be 41? Since these women are independent from each other, that's going to just be 0.99855 times 0.99855 5 times. So in other words, 0.99855 raised to the 5th power. So if I take 0.99855 and raise that to the 5th power, that's 0.99277. So question C. What is the probability that at least one of the 5 randomly selected 40-year-old females will not live to be 41 years old? In other words, if I randomly pick 5 women, what's the probability that at least one of them dies? So C, what is the probability that at least one of the 5 dies? Well, the probability that at least one of the 5 dies is the complement of all 5 live. All 5 living means that 0 die, right? So 1 minus the probability that 0 dies, which is again equivalent to all 5 living. So that would be 1 minus the probability we just found, 0.99277, and 1 minus 0.99277 is 0.00723. So if I randomly pick 5 40-year-old females, the probability that at least one of them dies before turning 41 is very low, 0.00723. Would it be unusual if at least one of the 5 randomly selected 40-year-old females did not live to be 41 years old? Well, that's way below 0.05, so the answer would be yes, this would be unusual.